Okay, I'm going to go through and do a demonstration of how you get from the Unity formula to an actual glaze. There's a number of different factors of the reason why I'm choosing this particular Unity, but included in with the oxides sheet, there is a limit, formula examples, and that is just basic limits for any glaze, really, for any temperature. And they're general limits. You can use, you know, maybe more or less silica or alumina. They're basic limits. What you will find is that this column here still needs to add up to 1. And then these two other columns are going to be proportional to this column. I've done a little bit of editing on mine. You can see I added La2O and to the KNaO, and then barium or strontium. I don't much use zinc in high fire glazes. Some people do. Especially in reduction glazes, it's probably not the best of ideas, just because it'll when it reduces, that actually will fume off and really not do much of anything. I know a lot of my glazes will have a higher silica content than this, so I just added the 3+ there. So these are like little additions that I've done just to kind of update it to what I think it needs. Okay, so with this in mind, I have this formula here. Okay, let's see if I can get them both in frame here. Okay, so I have my limit. This should all add up to 1, hopefully. I actually didn't add it all together, but it should add up to 1. We have 0.08 potassium, 0.04 sodium, 0.12 lithium. You can see the KNaO. This particular KNaO, which would be just the sodium potassium, would only be 0.12, but I've added the lithium into that, so I'm well within the KNaO guidelines there. And magnesium, you can have some or none. It doesn't really matter. Calcium, you can also have some or none. You probably do want to you probably do want to have a little calcium. Most glazes are going to have at least calcium in there, and I have 0.55. And then the barium or strontium, people aren't using barium so much, so they're subbing it for strontium. And this I'm going to have 0.14 strontium. Let's see. I need to add all this together. Hold it just a sec. Okay. Okay, let me see if this all adds up to 1 here. Oops, 0.08 plus 0.04 plus 0.12 plus 6 plus 0.55 plus 0.14. It's 0.99. So let's bump something up here. I'm going to bump the strontium up just a titch here. 0.15. That'll be an easy one to adjust there. My alumina is, you can see it's a little bit higher than this one. My silica is a little higher. It could be because I do have lithium and strontium. Those are pretty good melters, and I'm probably going to need something to melt, something to keep this from completely running off the piece. And so it has a little bit more alumina and silica than these things. You can also see that I have a 1:10 ratio here. It should be approximately 1 of these to 10 of these, so 0.2 to 2. Does that make sense? Hopefully it makes a little bit of sense. Okay, so we have this column adding up to 1. We have these. The reason why I picked this glaze is because it is a glaze that I use, and I want to see if I can make it out of thin air, if you will. All right, I'm going to move this out of the way. Hopefully I'm not bothering my camera too much here. Okay, so the first thing we're going to do is we need to write down our oxides across the top of the sheet here. Let me make sure I'm doing everything in the right order. I have a cheat sheet here. Where'd my cheat sheet go? Here it is. Okay, we need to reserve one of these for the molecular equivalent. Okay, and then we're going to do the oxides across. How many oxides do we have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we got K2O, Na2O, Li2O, MgO, CaO, SrO. So potassium, sodium, lithium, magnesium, calcium, strontium, Al2O3, and SiO2. We are inevitably going to have a few extra little things come up, but I'm not going to really worry about those things as long as they're not like a huge amount. We'll get to that when we get to that. Okay, so oh yeah, we need to write down the molecular equivalents that we need as well. So we've got 0.08, 0.04, lithium is 0.12, MgO is 0.06, calcium is 0.55, strontium is 0.15, 0.45 for alumina, and 3.28 for silica. Okay, so the reason why we're going to write all that stuff down there is so that we can keep track of it. What we're going to do is we're going to, one by one, or a couple materials at a time, we're going to go through and we're going to eliminate those and find a material that will fill all of those sort of at once. Okay, so I know this particular material has like a couple options for feldspars. So I guess if I didn't know that, I would just have to sort of look at the feldspar chart. There are a couple things to consider. The first is we need to fulfill potassium, sodium, and lithium. Okay, so lithium is kind of an outlier. We can get we can get sodium and potassium from other feldspars. Lithium, there's only one place there's only a couple places where we can get that. There's spodumene and petalite. So I'm going to choose one that might not bust some of our other materials. So let's look at our feldspar chart here. Okay. So what I'm going to look for, okay, we have lepidolite also. So lepidolite, I don't know if you can see that. There we go. That one has sodium and potassium in it, so I might avoid that one. It also has some manganese, some iron. Let's not use that one. Let's see. We need petalite, so that has some sodium and potassium. Has a lot of lithium. And then spodumene. Let's see, does this have more sodium and potassium in it? So 0.022, 0.26. Okay, so it's sort of a wash. Which has more alumina, which has more silica. Okay, petalite has a little bit less alumina. Let's see, 0.952. Petalite has more silica in it. I don't know, let's use petalite. So a lot of this is just sort of guessing. You'll find that pretty soon. Okay, so what we're going to do is I'm going to write down petalite here. And then we need to know the molecular equivalent that we need of petalite. And I think it's going to be, we have to actually divide the 0.870, or sorry, we have to divide the amount that we need by the amount that we are given in the material. So we need 0.12 divided by 0.870. So we need 0.138 molecular equivalents of petalite. Okay, so now what we have to do is kind of the same thing we had to do going the other direction, is we're going to times the molecular equivalent with all the materials that we have in the feldspar. Okay, so we got 0.138 oops. Point, move it over here so we can see what we're doing. 0.138 times 0.019 equals 0.003. Okay, so you see I'm going a little bit, I have one more decimal point, so I'll just add a decimal point there. So I'm going to do all my math and, to the thousandth so that we can be pretty accurate about this. So molecular equivalent, so 0.138 times 0.039 is 0.005. 0.112 times, oh sorry, oops, 0.138 times 0.870 should be 0.12. Okay, 0.06 times 0.138 is 0.008. Okay. 011 times 0.138 is 0.002. Okay, you'll notice that these are all written kind of in a funky order. They're not written the same order as what I have up here. For whatever reason, you just have to make sure that you're getting the right ones in the right column. That's kind of a tricky thing. I guess it's not that tricky, you just have to pay attention a little bit, but make sure you do get them in the right column. Okay, so 0.952 times 0.138 is 0.131. And then 7.77 times 0.138 is 1.072. Okay, so now we're going to draw a little line under here, under each of the things. Let's make sure that the lines are really nice and dark there so we can understand what's going on. So what we need to do is we need to subtract that from that. Okay, 0.080 minus 0.003, oops, is 0.077, okay? Minus 0.005, see, I did it again, 0.005 is 0.035. And so this one, we've spent that one. We've taken care of that. We don't have to do any more. 0.06 minus 0.08 is 0.052. 0.550 minus 0.002 is 0.548. We didn't do anything with the strontium, so we'll just leave that in its column. 0.450 minus 0.131 is 0.319, and then 3.280 minus 1.072 is 2.208. Okay, great. So we've taken care of lithium. Now we need to move on to probably sodium and potassium. The reason why we're keeping with the fluxes, these particular fluxes, is I know that I can get some alumina and silica and maybe some calcium magnesium, but to fulfill these two things, I need to use a feldspar. It'll probably give me negligible these materials, but it'll fulfill some of these other things. Well, hopefully it'll fulfill well, actually, it doesn't need to fulfill the alumina or silica because we can add those later. So what we need to focus on are these two now. So I'm going to skip a line. I'm looking at my ratio to potassium to sodium, and I have twice as much potassium as I do sodium, approximately. So what I'm going to need is to use a potassium feldspar. So I'm just going to go with Custer feldspar. And what I need is to fulfill the potassium. So I'm going to go back to my Custer feldspar page here. Okay, so I need 0.077. I'm going to divide by 0.664, and that will give me 0.116 molecular equivalents. And now that if I times all of those across here, I should fulfill hopefully potassium and sodium. If not, then we'll always think it should have. Okay, so as my grandpa would say, 116 times 0.664 is 0.077. Okay, that takes care of that one. 0.16 times 0.303 is 0.035. What do you know? Got rid of that one. Lithium, we've already gotten rid of it. Let's see. No magnesium, but we have some calcium. 0.033 times 0.16 is 0.004. Make sure we do it in the right column. Okay. Alumina times 1.043 is 0.121, and then silica is 7.133 times 0.116 is 8.827. Okay, now I'll just subtract these ones. So we got 0.544. And we got, okay, 8. Okay, let's do some math here. That's probably 9.229 or something. 298. I'm going to subtract just in case. 319 minus 121. 0.198. 2.208 minus 0.827 is 1.381. Okay, great. Now we know what we need to focus on. I'm actually going to do, the next one I'm going to do is going to be, so the reason why I'm not focusing on calcium, magnesium, and strontium, especially calcium, I can get calcium, I can get strontium, or sorry, calcium, strontium, and silica. I need to make that more of a silica. Okay, I can get calcium, strontium, and silica as single elements. Magnesium, I'm probably going to get that with calcium. So I'm going to go for the complex elements first. I think I may have not mentioned that. Just go over the complex elements first. So this next one, I'm going to go with EPK. okay? Because I want to go for alumina, and when I use a clay, I'm going to go for alumina. I'll get alumina and silica, also maybe some other negligible things over here, but let's not worry about that quite yet. So alumina, I need 0.198, so I'm going to divide 0.198 by how much, so actually I need 0.198. The reason for that is because alumina clays are unity to alumina as 1. So if I divide 198 by how much I need, 0.198 by 1, I'm going to get 0.198. Hopefully that makes a little bit of sense. So now I'm just going to go through and times everything across. Now, I'm probably going to get a little bit of potassium and sodium. It's not that big of a deal. I could go back and change this just a little bit, but I don't think it's going to be I don't think it's going to be enough to really change anything. Oops. Times is 0.002. So that's kind of over a little bit. It's fine. 0.012 times 0.198 is 0.002 for calcium. And same with magnesium. Okay, alumina will be 0.198, and then silica will be 2.098. That is 0.415, 0.415. Okay. Okay, so that's, oh yeah, we gotta subtract here. So 0.052 minus 0.002 is going to be 0.050. Okay, 0.542. That's going to be done. And then 1.381 minus 0.415 is 0.966. Okay, so now we have the last things that we need to get. Again, these two I can get on their own. Oh, I guess we have three things we need to get. We need calcium, strontium, or magnesium, calcium, strontium, silica. Silica I can get on its own, calcium I can get its own, strontium I can get its own. Magnesium usually comes with calcium or silica, so I could either do, for the magnesium, I could either, because I still have a little silica left, I could do talc. Maybe let's do talc, just for the heck of it. I don't think that's actually I wonder if that's in the recipe. We'll find out when we go back to the recipe. So talc. So for the magnesium, I need 0.050. So what I'll do is I'll go to talc on here. And so if you look, I have 3 magnesiums in my talc and 4 silica and a water. That's the raw formula. What we actually need to look at is the fired formula. Okay, that's the most important. Okay, so it's molecular weight and equivalent weight. Okay, those will be important later. What we actually need is the unity. So we're going to go with 3 magnesiums and 4 silica. So I need that much. I need to divide by 3. Is 0.017. Okay, so 0.017 times 3 magnesiums is going to be 0.05. Okay, 0.017 times, can you see that? Yeah, For silicas, it's 0.068. Okay, so I'll subtract again. That's going to cancel the magnesium out. I'm still going to have 0.898 in the silica. So here, this is going to be maybe a little confusing. Like for my magnesium, I could have either done talc or dolomite. I just chose talc because it fulfills another column. If chemically they're the same, they will look exactly the same in the firing, as long as the materials are ground properly. So I could have chosen dolomite, which has, let's see, where's my other page? Okay. Where's dolomite? Why is there no dolomite down here? Cryolite? Feldspars? I don't know why dolomite's not on here. But anyway, dolomite is 1 magnesium and 1 calcium. I don't know if I'm just like blind right now or if it's just not on here. It's just so weird if it's not on here. Some silicate. Huh. Alright, well, whatever. I guess it's not on there. It's a good thing we used talc because it would have been really confusing. Okay, so now we still need strontium. We still need some calcium. So make sure you go down the column and find the X's. If there's no X at the bottom of the column, we still need to find it. So strontium's still way up here. We haven't done anything with that. Poor little strontium. Okay, so we can just knock these out one by one. You can see that each time I do this, I'm skipping 2 lines. So let's go whiting. We need 0.542. And whiting is 1 calcium, so we'll just go 0.542, and that cancels that out. Okay, the next one we need to do is strontium. And we need 0.150, and strontium is, which page are you on, strontium? Strontium carbonate. It's just one SRO. So, yeah, so we're just going to times it by 1, 0.150. That'll X that out. Alumina's X'd. Now silica. So we go flint, silica, UICA. Still in the frame there. So I need 0.898. And then it's just 1 silica, so oops, 0.898, and that'll X that out. Okay, so now we have all of the molecular equivalents of all the materials that we need. Now what we can do is we're going to move up, or we're going to move into this frame here. Okay, so we're going to rewrite all the materials and their molecular equivalent, 0.138, Custer, 0.116, EPK, 0.198, talc is 0.017, whiting 0.542, strontium is 0.150, and flint, that all still, yeah, okay, all still in the frame here, just to kind of make sure we're still recording it here. 8. 898. Okay. I'm just going to double check to make sure that I have all my columns checked off there. Okay, I do. Okay, so they're equivalent weights. That's where these other sort of charts come in. Okay, so equivalent weight of petalite. Let's see here. So whatever, so you might actually find that petalite is actually on here as well. If you're using this to go one direction, make sure you use this to go the other direction. I used a more complicated version, just for kicks, I guess. I don't know. I actually used this version. With this, my equivalent molecular weight is 599.38. Okay, Custer is 620, oops, 620.68. EPK is 270.319. Talc okay, so this might be confusing. We have the molecular weight and the equivalent weight. So basically what it's doing is it's whatever, I don't know, somebody decided that its equivalent weight was this particular number. I think it has to do with this water leaving, even though it's like way less than half. I don't know who decided that, but that is going to be our equivalent weight. Make sure you're using the equivalent weight, not the molecular weight. They're going to be different. Sometimes when they fire, when they get fired, they change structure, and so that's going to affect the molecular weight. Okay, so 126 is going to be our equivalent weight. Whiting, so that's calcium carbonate. I think that's what they call it here. Calcium carbonate is 100. Strontium is 148. And flint is 60. Okay, so now I have all the equivalents. Now you times just straight across to get parts by weight. 0.138 times 599.38 equals 82.70. Okay. 6 times 620.68 equals, so I'm just going to call it 72.00 because it's 9.99. And rounding up. Okay, 0.198 times 270.319 is 53.52. 0.017 times 126 is 2.142. It's not very much. 0.542 times 100 is 54.2. 0.150 times 148 is 22.2. 0.898 times 60 is 53.88. Okay, you could actually, right at this point, you could take that many grams of each of these things and mix it together, and you could have a glaze basically. But to get it to an actual percentage, we're going to do just a little bit more math. So we're going to add all of these columns together. I'm going to go up Now I have to go down so we're not confusing everybody. Okay, 82.7 plus 72 plus 53 plus 2.142 plus 54.2 plus 22.2 plus 53.88 equals. So in this column, total parts by weight, we're going to go 340.642. Now we need to divide. It's a lot of math and just arithmetic basically, but we need to divide all of these numbers by that number. Okay, this is where the scientific calculator comes in, but we'll just type it all in because I don't have a memory in this calculator. 82.70 divided by 340.642 is 0.2424. I'm just going to go 3 decimal places. I'm probably not going to go more than 1 decimal place when I get to that. So 72 divided by 340.642 is 21.14. Sorry, 0.21. Actually, 211. 53.52 divided by 340.642 is 0. So that's a 2 there. Okay. 157. 2.142 divided by is 0.06. That's a very small amount. 54.2 divided by 340. 1.77. Sorry, 1 point. That can't be right. 54.2 divided by 340.642. There we go. 0.159. Okay, one last one. 53.88 divided by 340.642 is 0.158. Okay, so with any luck, all this will add up to 100 when we get over here. All this should add up to 1. Okay, so now what we need to do from unity, so this all adds up to 1. What we need to do is add up to 100. So what we're going to do is just going to move the decimal places 2 places. Or times it. You can go through and times everything by 100 if you really want to, but if you just want to move the decimal places, that's great. 24.3, 21.1, 15.7, 0.6, 15.9, 6.5, and 15.8. Let's add all those together and make sure we got 100. Yeah, close enough, 99.9. That'll do, I guess. Okay. So these are in kind of a funky order, and I don't really have my actual recipe handy, but this right here is our new recipe. So you can go from Unity to a recipe. Now this can come in handy if you just want to sort of, fudge an old recipe from glossy to matte or vice versa. You can theoretically get like a chemical composition of an ancient Chinese or Japanese glaze. You can go from that chemical composition to unity to this. There's a lot of different things that you can do with this. Another thing, yeah, and then once you get here, you can just like basically you can just go right in the lab and mix this up. So there's that. I hope that was sort of informative. I guess if you yeah, have any questions, I guess we'll talk about those in class. Yeah, thanks for watching.